All right, marvelous AP Calculus AB students. You guys have completed the entire year's worth of material. Or maybe it should be better said, you have learned everything that you've needed to learn throughout this year in AP Calculus AB. However, there might be one or two of you that may have forgotten one or two topics throughout the year. So I always like to finish up the time before the AP exam doing a little bit of review. So you guys have 9 review days ahead of you. This is the first of our 9. Each of our review days is going to be based off of a particular type of free response question that you might see on the AP exam. So I've seen some teachers and some calculus gurus post about how there are maybe like 6 types of questions or 7. I've divided mine into 9 or so possible types. And what do I mean by types? Well, we should know the number of free response questions on the AP exam, right? There are 6 questions. We also need to know that 2 of those questions, the first 2, 1 and 2, are calculator active, and then the last 4 are no calculator. We also need to realize that each question is allotted 15 minutes with a grand total of 90 minutes. You'll do 30 minutes, put away your calculators, and do another 60. Now, each of these free response questions are also worth 9 points, which means you're going for a total of 54 points. Now, we don't actually expect you to get 54 points, so that would be brilliant if you do. There are about 10 or so perfect scores on AB every year, and that could be you. Realistically, what's a good number of points to be getting on each free response question? I'd say you should shoot for about 50% of them, so maybe 27 points, or what does that break down to? Between 4 and 5 points on each problem. That's pretty darn doable. I'd say 3 or so points on one free response question. And remember, each free response question has parts, usually parts A through D, sometimes just A, B, and C. We don't know the number of points in each of those. I'd say an average number of points is probably 2 points per problem. Sometimes there's only 1, sometimes more than 2, but on average 2 points per problem. You should be able to get at least 3 points. And those 3 points really just come from setting up each of the problems. Sometimes there's a gimme where the setup and the answer is very easy, but the setup should be fine. If you can find 3 points out of 9 on those 6, giving you 18 points, you're doing great. If you can find 27 points, you're doing phenomenally. Right? 27 points is actually generally the lower end of, well, probably the upper end of a 2 score most years. It varies year to year. So as long as you don't get a 0 on the multiple choice, you should be just fine. But either way, you're looking for the setup. Now, what is the point of these 9 review days? Well, if there's only 6 free response questions, and they're going to try and test you on pretty much everything in the entire course, 6 free response questions, 4 parts apiece, there's only 24 parts. And it's really hard to fit in AP Calculus into those 24 parts. There's some things that just probably won't show up on those 24 parts that are just going to be tested in the multiple choice, but I like to think usually they attempt to test everything twice on the AP exam, once on the multiple choice, once on the free response. And so what we found is that in order for College Board or AP to test you on those things, they have some fairly predictable free responses. So it's my goal after these 9 for you guys to go through, pick up a practice test, pick up some release free responses, and turn to one and go, oh, we'll just look at this one, that's where they gave us the graph of f prime. Or you pick up another one and go, oh, that's a rate in, rate out. Or you pick up another one and go, oh, that's a volume and revolution problem. Very cool. So if you want to treat these 9 as reviewing the whole course, you can. It doesn't go in order that we learned everything. It goes in the order that I put these together. But we are going to start today with the first AP targeted review, generally through free responses. We'll throw some multiple choice in there every now and then, but free responses work just fine. And our first stop is interpreting graphs of f prime. This is probably the most consistently asked style of question every year for the last almost 60 years now. The AP exam for calculus is pretty old. the idea is that they will give you a graph of f prime. In fact, let's look at this first one. This comes from 2017. They gave us the graph of f prime. And then what do they want to know? Well, they want to know things about the graph of f. So they're going to ask you to identify characteristics of f prime to tell them things about f of x. Now at the start of each of these reviews, I'm going to give you just some reminders or some hints, and actually I'm going to go back to these at the very end just to make sure we've accomplished all of this throughout what we've done today. It's a little bit harder to read through these and imagine what's happening, so we're going to do some concrete examples, then finish off and make sure you're comfortable with the summary at the beginning. Now, you also will notice that there are two free response problems here. The first one takes 2 pages, the second one takes 2 pages, and that's about the length of each day. Sometimes they're a little bit shorter. You also might notice, though, that my first free response has A, B, C, D, E, and F. So you might be thinking, whoa, that's a really long free response. Well, that's because this is longer than the actual 2017 question 3. I added some parts in here to make sure that you got a very well-rounded look at all the different parts they could ask on a problem like this. And then on the next one, I've tried not to repeat myself too much, but there is certainly some repetition. But this is a similar question asked in the same way, so I made sure that you were able to practice maybe some additional items that weren't asked in the first one, or some similar ones but asked in a different way. Now, you'll notice that this video is pretty long, right? It's closer to 60 minutes or so, and I would not expect you to watch all of it because you already know how to do everything in these videos. What I'd really expect you to do is to try these problems on your own. In fact, I've posted all the worked out solutions on Teams, and you can take a look through there. Or if you don't want to look at Teams and you're like, I'm really stuck on, part C, then just skim my video to C and let it help you out. But your goal is to be able to correctly complete all of these, and if you can do that without watching the video, then please do it, right? There's 2 free response questions. It should take you about 15 minutes per each one, maybe a little bit more because I added those on. But yeah, I would say at this point, really pause the video, go through, finish what you can on the first one, check your answers, watch any parts of the video that help you, and then move on to the second. Let's go ahead and get to this together, though. The function f is differentiable. And reminders, if f is differentiable, we have f prime down here, f being differentiable means not only is f continuous, right, you can draw the whole graph without picking up your pen, it also means that the derivative of f exists everywhere. So it means that f prime exists, sometimes you'll hear it called defined, at all points. Why does f prime have to exist at all points? It has to exist at all points because differentiable means that f has slopes at all points. Now, looking at this graph, because this is a really common misconception, people look at this and go, but f prime doesn't exist at all points. Look, there's a sharp point right there. That means that f prime doesn't exist. Well, you're really just mixing up 2 different knowledge zones, one from before calculus and one in calculus. A point exists if there is a point there. Therefore, we would write this point in function notation as f prime of 3 equals 2. F prime exists at 3. The output is 2. There is a point there. So what's this sharp point thing where things don't exist? Well, that is the derivative of a given graph. So how would we write the derivative of this graph? Well, if this is f prime, then we get to f double prime. F double prime of 3 does not exist because of that sharp point. We're actually going to come back to this later, but it's very important to, pun intended, differentiate between when a slope exists because of a sharp point versus when a point just exists. If there's a point there, then that means whatever this graph is, in this case f prime, exists at that point. All right, it is very common for a problem like this to give you 1 point on the original graph. And in this case, they told us f of -2 is 7. -2, 7 would be way up here. It's not on this graph. This is f prime. And also, they told us how f prime is created, 3 line segments and a semicircle. Let's start with a very, very common question. Find the values on the graph of f using, or on the graph or function of f using the graph of f prime. This is manipulation of the fundamental theorem of calculus. I see 2 points we need to find, so I'm going to split my paper in half. We'll start with f of negative 6. Usually, and this is not a hard rule, more like a guideline, the first point asked for has less work. The second point asked for has more work. With that in mind, you might want to split your paper a little bit more like this, but you don't have to. I'll keep it right in the middle because I did that first. So f of negative 6, how do we do it? Well, we need to go from f prime to f, which means antiderivative, which means integral. When we integrate, because we don't have an equation, we're going to need to do something with area. No equation, it's all about area. So we know we need to incorporate negative 6. What else am I going to incorporate? Oh, that's right. The only other thing I know about f, the point at negative 2. So I'm going to go from negative 6 to negative 2, f prime of x dx. And we know by the fundamental theorem that that will be f of negative 2 minus f of negative 6. You could have gone in a different order. You could have done negative 2 on the bottom, negative 6 on the top. I always like to go least to greatest, though, moving left to right, right? Negative 6 to negative 2. So moving this way, I think that makes your life a little easier. Now, when I set up the second one with 5, right, I'm going to, again, use the point given to us, negative 2 and 5. Negative 2 now is going to go on the bottom of my integral because that is smaller than 5. And we get f of 5 minus f of negative 2. This jogs your memory. Go ahead and finish off the problem. If you want to keep watching, you can. It's now all about isolating and finding areas. So let's isolate first. We're looking for f of negative 6. I'm going to add that to the left side and subtract the integral to the right. F of negative 6 is going to be f of negative 2 minus the integral from negative 6 to 2, f prime of x dx. Same thing over here. If I'm looking for f of 5, now I'm just going to add f of negative 2 over to the integral. Keep that all on one side there. There we go. Once we're here, it's just a matter of substituting in the values we know, or that we can find. We know that f of negative 2 is 7, right? And we'll keep working this way. I'm going to actually space this one out. I might need a little bit more room here on the left side. So we know this is 7. But what do we do with the integrals? Well, if we had an equation, we'd use the fundamental theorem. We'd actually do the antiderivative. But we need to remember there are 2 ways you can evaluate a definite integral. One is through antiderivatives, but the other is through area. And so, how do we find the area? Well, we look up at the graph. From negative 6 to, that should be a negative 2, awkward. From negative 6 to negative 2, the area is just, between the function and the x-axis, that looks like a triangle to me, doesn't it? Our area is 1/2. That is a base of 4 if you count over, and then a height of 2, and so that looks like 4. Not bad. Okay. And then we also have some other areas to deal with. Notice that this guy, from negative 2 to 5, negative 2 is right here, 5 is over here, and so we actually have 2 areas, right? So let's do this semicircle first. We know area of a semicircle, a whole circle is pi times the radius squared, but half a circle needs a half in front. And then what's the radius here? Well, the radius is from the center to the exterior, so the radius is 2. And then don't forget that this semicircle is below the x-axis, so I think we need a negative on that. 4 divided by 2 is 2. That looks like negative 2 pi. Last but not least, we also have this triangle up here. It is okay to divide this into 2 separate triangles. I actually prefer it as one triangle, one equation that way, right? And so with our one triangle, the base is certainly, and I'll do this, the base is certainly 3. But the height, well, the height can be drawn by a perpendicular line from the tallest point of the triangle to the x-axis, and that is a height of 2. And so half of 6 is 3. All right, we have our areas. Let's fill them in. From negative 6 to negative 2 is just an area of 4. And so doing a little mental math here, f of negative 6 is 3. Looking the other way, we have this negative 2 pi, right? There's a plus in between, and then we have a plus 3. And cleaning this up as well, f of 5 then, 7 and 3 is 10, minus 2 pi. I heavily suggest you do not turn this into a decimal. They're looking for exact answers here. This style of problem will almost always be no calculator. The reason it's no calculator isn't because they're trying to punish you and make you do math without a calculator. It's that there are a bunch of problems that they want to put on the calculator active section where you have to use a calculator to solve it, and they want to test your calculator skills. A calculator really doesn't help at all with a graph like this, and so you should expect to see out of the last 4 free responses, right, the no calculator ones, one of them will be the graph of f prime. All right, it's almost guaranteed it'll be there. Of course, now that I say that, watch it not show up, but you should really not be surprised when a problem like this comes up. Great, we have those two. You also might notice that I didn't box my answers. It is suggested at times that students don't box their answers. In problems like this, there's nothing wrong with it. I will also tell you, and we should finish the boxing the answers first. So let's say that you were asked to find the equation of they asked you the slope of a tangent line. And so you're looking at your graph and you're like, okay, slope of a tangent line, that means I need to write a tangent line. You find the slope is 5, and I'm just making all this up right now, and you box this answer. Well, you actually would get that wrong, because if they ask you to find the slope of the tangent, they just want the slope right there, don't they? Right? So if you did something like you found, let's call it f prime, like f prime of 1 is 5. That's the slope of the tangent right here. If that's your answer, but then you continue and you use the slope in your tangent and you box it, now you're boxing something. You're saying, I think that's the slope of the tangent line. Well, that's not. That's the equation for the tangent line. The slope's up here. And so if you had boxed this, full points. If you box this, you'd lose a point for the answer. And if you box nothing, full points. Because it's great that you could write a tangent line here, but you found the slope earlier, and that's what they're looking for. So as long as you don't box the wrong answer, you're fine. But that can get you into trouble sometimes. The other thing that is worth mentioning is simplifying. Ooh, simplifying. As soon as you get to a spot where you can type that into a calculator, whether the calculator on your phone or even a basic scientific calculator, you can stop. And so if you wanted to stop right here and not write this last line, great. That's 100% full points, right? If you don't trust yourself on basic addition, subtraction, anything like that, then you don't need to simplify. Same thing. If you wanted to stop right here, if you're like, I don't know if I can combine those as like terms, then stop right there. But as soon as you go the next step, you better make sure that your next step is correct, because if you get the next step wrong, even if this first step was right, you will lose the point for your answer. All right, let's go ahead and move on to critical points. A friendly reminder, critical points of a graph, in this case the graph of f, are found by determining where f prime, or the derivative of the given equation, is equal to 0, or where f prime does not exist. And you need to look at both. Now, where is f prime equal to 0? Well, looking up at our graph here, I'm going to erase some of these calculations because they might get in the way later on. I'll keep the areas. We might want those, but I think everything else can go. Where is f prime equal to 0? Well, if you had the equation, let's say you had something like, I don't know, x squared plus 6x plus 8 equals 0, and they asked you to solve that equation. Well, one way is you could algebraically solve. But if you had your graphing calculator, couldn't you graph this equation and find the zeros? Aren't zeros of a graph where the graph crosses the x-axis? Okay, and so looking at this, I think my zeros here are at -2, 2, and 5. So the answer is going to be x equals -2, 2, and 5. Couple things to note. They said only look between -6 and 5. These parentheses mean don't include, so I'm actually not going to include 5. And then oftentimes I usually don't close the second curly brace because we'd also want to look to see where f prime is undefined. So looking up here, is there any place where f prime is undefined? What does something undefined look like? Well, it's really where there's going to be an open circle. It's where you have to pick up your pencil. And it's a little bit further than that too. It's not just that you have to pick up your pencil, because sometimes you can have things that have an open circle here and then are defined over here. That'd be okay. It'd really, though, be something like this. 2 open circles, there's literally no point at -2. That would be undefined. But this is defined everywhere. There, any x value you give me, like I don't know, -4, that's defined. There's a point there, right? There's a point everywhere on this graph, so there's nothing here. In fact, I would probably center this. I'd say if we wanted to solve all of this at once, the only two values we need to consider are those two. Okay, now what? Well, justify if those critical points are relative maxes, mins, or neither. I'm going to go ahead then and just make a quick sign chart. That's how we've justified in the past. No reason to change. -6 to 5, -2 caused f prime to be 0, 2 caused f prime to be 0, and we can go ahead and test points. But f prime, if we're looking for the sign of f prime, it's a sign chart. Signs of a graph are just if the graph is positive or negative. So positive, negative, positive, right? Above, below, above. So we have positive, negative, positive. I'll keep trying to use red for f prime. What does this tell us? Sorry, I'm going to use red for f. My bad. What does this tell us about f? Well, it tells us that f is increasing, then decreasing, then increasing. That gives us a pretty nice picture of f. So let's go ahead and interpret our results. Okay, we would say something along the lines of x equals -2 is a, well, based on this, it's got to be a relative max, doesn't it? Is a relative max because, how do we know that's a relative max? Well, we know because our sign chart told us, and so that's what we're going to write in our sign chart, because f prime of x changes from positive to negative at x equals -2. You probably don't need this part at the end. I always put it just to be very clear about what I'm talking about. Some people will say, well, wait, instead of saying positive and negative, could I do plus and minus? Sure. There's nothing wrong with that. Is there anything you can't do? Yeah. The one thing you can't do is you can't say increasing to decreasing. That's just not right. All right. Increasing means positive slope, and f prime does not change from a positive slope to a negative slope at -2. This is a negative slope that I circled first, and this is still a negative slope, right? We're going down, and then we continue going down this graph. So we can't do that increasing, decreasing. That'll come in later on once we start talking about the slopes of f prime. But yeah, I'd just say write what's in your sign chart, and you'll be fine. What about the other one? Well, same idea. X equals 2 is a relative min because f prime of x changes from, this time it's got to be negative to positive at x equals 2. Great. Done. Nothing bad. Very, very common. We need to be comfortable with that. Part C. Find the absolute minimum value of f on the closed interval. Justify your answer. Okay, well, there are two ways to find an absolute minimum. One of them is known affectionately as the lonely critical point theorem. We're not going to touch on that today. Instead, we're going to do the thing that works every time. It can be a little more time-consuming sometimes, but for today, I think you'll find it a nice review. The way we find absolute minimums or absolute extrema in general is the candidate's test. In order to perform the candidate's test, we need to set up the candidates. We are going to try all the possible places where the lowest point on f can occur. Those can occur at endpoints, -6 and 5, but they can also occur at critical points. Where are the critical points? Oh, wait, we found those in B. That's so exciting. The critical points are at -2 and 2. Be very careful if part B didn't exist. Part of your justification needs to be where these two were found. -6 and 5 are obvious. It's the endpoints. How did we find those? Well, we don't need to write this because we did it in B, but you would have to say f prime of x equals 0 or does not exist, maybe an arrow for implies, when x equals -2 and 2. It is required to get full points that you explain you used f prime to find the critical points. Don't just pull those critical points out of a hat. All right. From here, and again, we don't need it because we did it on B, but from here, we need to actually find all the different outputs and then choose the smallest. Now, what I really like that the AP exam's been doing recently is they've actually made you do most of this work earlier on, right? In particular, f of -2, they gave that to us. That's 7. That's nice. And then what about these others? Well, on part A, we had to find f of -6 and 5. Those were the endpoints. That's awesome. F of -6 ended up being 3, and 5 ended up being 10 minus 2 pi. All right. Well, let's make sure I got those right. 3 and 10 minus 2 pi. Excellent. So I think there's only one more to find. But how do we find this one? Well, isn't this the same as part A where they asked us to find values? So if we wanted to find f of 2, then we're going to use the integral. We're going to use the point that we know, smallest to the point that we want. That's the largest in this case. And we're going to manipulate that fundamental theorem. Watch those primes versus not primes. We're looking for f of 2, so I'll add off the f of negative 2 to the other side. Something like this. Equals f of 2. Excellent. F of negative 2 we know is 7. What about from negative 2 to 2? Well, negative 2 to 2 is an area, and oh look, we already found the area. It's negative 2 pi. That's exciting. So 7 plus negative 2 pi equals f of 2. 7 minus 2 pi. Pretty much done here. We just need to actually tell them which is the absolute min, right? We've written a chart, but we haven't actually answered the question. Find the absolute min. Which is it? Well, using our sign chart, we can narrow it down. We know it's either this guy or this one. So this guy or this one. But which one's smaller? Well, we're going to pull the engineer route. It's kind of a joke about engineers. They like to round pi to be 3, make it a little easier for calculations. 7 minus 6 is 1. What's smaller, 3 or 1? I'm pretty sure 1 is smaller. We don't want to keep this up here, though, especially this equal sign. Or especially saying that maybe these are equal to each other. So I think all we really need to do here is realize that this is 1. And then instead of erasing it, it's much faster just to cross out. If you cross something out on the AP exam, they can't read it. They can't hold it against you. It can't help you either. But if you write a quick calculation that's a super approximation, you need help doing the math, I suggest you cross it out after just so they can't hold it against you. And then we're going to finish it off here by just saying that this is the absolute min. Nothing bad at all. Now, once we're here, are we done? Because the problem asked us to justify our answer. Well, actually, this table over here for the candidates test is our justification, which is really, really nice. We don't need to write any sentences here. We showed the candidates, we found the outputs, and we labeled the absolute min, the end. Some people say, well, can I write a sentence? Sure. If you feel so inclined, we would say something like the absolute min is 7 minus 2 pi. You could be an overachiever, and you could say, and occurs at x equals 2. But if they ask for the value, they just want the output. Some of these will just ask for the location, though. And a lot of times you can use a sign chart, and we'll see this later on, not today, but another class. You can use a sign chart just to find the x value if you don't need the y. All right, moving on. Part D. For each of f double prime, blah, 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 find the value or explain why the value does not exist. So I'll go ahead and again split my paper. Nice for clarity. You want to be nice to the readers. If they see you've neatly organized everything, they'll be nicer to you. Maybe not, but it's nicer as a reader to see an organized paper. We're going to find each of these. So we need to find f double prime of negative 5, and we also need to find f double prime of 3. F double prime of negative 5, f double prime of 3. Remember those numbers, negative 5 and 3. We'll take a look in green. Negative 1, 2, 3, 4, 5, and 1, 2, 3. All right, let's start with this guy over here. They are asking us for the value of f double prime of negative 5. Well, we have f prime. How do we find f double prime? Well, this is the derivative of f prime, and the derivative always measures the slope. All right, so if we're trying to find the slope, then, well, this is luckily a line. I think slope of a line is pretty easy, isn't it? Down 2 over 4. So I think this value will just be down 2 over 4. Now you might be shrieking in terror saying, oh my gosh, you wrote the fraction negative 2/4. Isn't that actually the fraction negative 1/2? Sure. And if you want to reduce, you can. But you do not need to reduce on the AP exam. Right? 5th grade and reducing fractions was a lie. No, it wasn't. You should still be able to reduce a fraction. But yeah, that's all we need here. This is just negative 1/2 or negative 2/4 if you're being a rebel. Does it ask us to justify the value? No. F double prime of 3. Let's see, f double prime of 3. Oh, we talked about this earlier, didn't we? Right? Foreshadowing. This is a sharp point. This is not going to exist. Two things about that. First, I'm not going to put equal signs. We only use equals when we equal a value. Does not exist is not a value. It's the lack of a value. Same way, infinity is not a value. We don't equal infinity. So f double prime of 3 does not exist. Sharp point. Now, what do we do down here? Well, the very first thing we're going to say is f double prime of 3 does not exist to answer that question. But then they explain why the value does not exist. And this we need to take a little further. Because although there are several justifications that sometimes receive credit, sharp point, 2 line segments with different slopes, something like that, the one way you can receive full credit for explaining why a point does not exist, why a slope doesn't exist, is with two-sided limits, or rather one-sided limits to prove a two-sided limit does not exist. So what does that look like? Well, we should show this with pretty pictures up here. We are going to discuss this point, and in particular, we are going to look at the left side and the right side here, but we're not going to look at the values because the limit as x approaches 3 from both sides of f prime of x, this is the graph of f prime. The value it approaches is 2. That limit does exist. We want to look at the limit of f double prime. F double prime is the slope of this graph. So if I wanted to look on the right side, so as we approach the next value of 3 from the right side of f double prime, what are all the slopes on the right side? Well, this goes down 2 and over 2, so negative 2 over 2, or if you're feeling bold, negative 1. So the slopes on the left side are constantly negative 1. However, the slopes on the right side, the limit as x approaches 3, the left side of f double prime of x are over 1 up 2. This one looks like 1/2. Nope, rise over run. Up 2 over 1, isn't it? 2 over 1, or just 2. If the limit of the slopes are not equal, then the slope at that point does not exist. Okay, so how do we conclude this? We would say something like, does not exist because the limit as x approaches 3 of f double prime of x does not exist. And if you wanted to go further, you would say something like, the limit as x approaches 3 from the left side equals, I think that was 2 over 1, that was 2. And the limit, maybe we'll even put a not equal in the middle, and the limit as x approaches 3 from the right side of f double prime of x equaled negative 1. The left side and the right side weren't equal, the overall limit doesn't exist, and so that point doesn't exist. Do they always ask you to justify? No. 2 years ago, 2018, they just said, find the value or state that it does not exist. And if it's state, then just put does not exist and be done with it. But if they do ask you to justify a slope, the expectation is that you use one-sided limits. All right, identify the inflection points for f and justify your answer. Seems pretty similar to critical points, doesn't it? So we start with f double prime of x, right? Inflection points have to do with the second derivative, or f double prime of x does not exist. Okay, let's start filling these in. Where is f double prime, which is the slope of f prime? We're not going to need these areas anymore, so I'm going to go ahead and clean up my graph. Where does the slope of this graph equal 0? Well, I think there's only one spot right here. There's a slope of 0, a horizontal tangent line, rate 1, x is 0. So x is 0 is 1 point we'll have to keep track of. Are there any places where the slope of this graph, where f double prime doesn't exist? Yeah, 1, 2, 3. 3 more of those. It's negative 2, 2, and 3. Let's put all those together for our answer. Negative 2, 0, 2, and 3. X equals negative 2, 0, 2, and 3. So then are we done? It says justify your answer. Couldn't I just say that those 4 points are the inflection points because f double prime is 0, f double prime doesn't exist? Hopefully you're saying, no, 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 I remember there's something else about inflection points. We also need to know if the points, or if f double prime changes sign at those points. So let's quickly go through here. Let's make a nice sign chart for f double prime of x. We're looking from, it was negative 6 to 5, is that right? Negative 6 to 5, all right. Negative 6 to 5. Here's negative 2, 0, 2, and 3. I remember that 0 had a slope of 0. The rest of these were all does not exist. You're, of course, not graded on your sign chart, so you can put this in if you'd like. I usually turn my paper, or in this case my tablet, sideways so I don't take up too much room, and we can say it does not exist, DNE. It's hard to read sideways. Okay, and then how do we fill in the signs? Well, f double prime of x are the slopes of f prime. So what characteristics of this graph show us the slopes of f prime? Well, just by looking at the slope. My first slope here, this is where f prime is decreasing, right? Decreasing is going to be a negative slope. This is also decreasing, but then afterwards we start to increase. We increase some more, and then we again decrease at the end. So negative, negative, positive, positive, negative. All right, finishing this off, we had negative, negative, positive, positive, negative. And if we wanted to look at the graph of f from f double prime, so it would tell us that f is concave down, then concave up, then concave down. Where does concavity actually change sign? Concavity only changes sign at 2 of those 4 x values, at 0 and 3. And so if you had listed all of these, you would have been wrong. There are not 4 inflection points, rather there are only 2. So f has points of inflection at x equals 0 and 3, justify, because, well, how did we know the signs of f double prime? We actually don't want to read straight through our sign chart here, because the graders would say, if you tell them, because f double prime changes from negative to positive or positive to negative, their question would be, how do you know anything about f prime? We gave you the graph of, or f double prime, we gave you the graph of f. And so, although you could write a nice sentence about, oh, well, f double prime measures the slopes of f prime and blah, 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 it's much faster and preferred for you to just use the graph of f prime to justify. So how did we know the signs of f double prime from the graph of f prime? Well, I actually wrote it on the graph for us. That's where f prime changed from decreasing to increasing, or from increasing to decreasing. Not f prime changing from positive to negative. That's for our critical points, but this is where we use our increasing, decreasing. So because f prime of x changed, or changes, from, almost did it backwards, from increasing to decreasing, or vice versa, at x equals 0 and 3. And again, you could probably stop right here if you wanted. I always put the points again at the end just to reaffirm, pun intended, the point. But either way, that's what we're looking for there, right? Whatever they give us, whatever equation, whatever graph is what we use to justify our answers. Last but not least, write the equation of the line tangent to the graph of y equals f of x at x equals negative 2. Tangent line, we can do that. We're experts by now. T of x equals, we need to find the derivative, f prime at negative 2, that'll give us our slope, times x, 2 negatives make a positive, and then we need an output of f of negative 2. All right, nothing bad here. We'll leave a nice little blank, x plus 2. Then f of negative 2, I think that's 7. That's given to us. We've used that a bunch. How do we find f prime of negative 2? Probably has to do with the graph, so if we jump back up here, f prime of negative 2, where is negative 2 on here? Oh, that's this guy right here. Ooh, sharp point. Doesn't that mean does not exist? No. If it was f double prime of negative 2, it would be does not exist. This point has an output. This is a point negative 2, 0. So we know that f prime of negative 2 is 0. 0 is a number. So we end up with this. And I would stop right there. You can box it if you're feeling bold. If you're feeling super gutsy, you can try and simplify. You can do 0 times that plus 7, which is just 7. Either of these are fine. However, I would prefer you just stop here. Don't make a mistake. Don't say 0 times something is 1 and get 8 or something weird. Just keep it easy. Well, we are now on to our second of just 2 problems for today. Again, hopefully you guys are just flying through this on your own and not listening to this whole video. Your brain is much more actively engaged when you're doing the work, not listening to some weird foreign voice explain the work to you. So, let's get to it. 2012, problem 3, continuous function, graph consisting of 3 line segments and a semicircle, very similar to the last one, given below. Now you might be looking at this saying, but they gave us the graph of f. That's weird. I thought you said we'd be given the graph of f prime. Well, this is kind of the same thing, just phrased in a different way, right? You're never just going to be given the graph of f and then asked questions about f. I mean, that'd be silly. If they said, where is the absolute max of f? You'd be like, here. There's no calculus. So what do? Well, they give us the function g. G is given by g of x equals the integral from 1 to x f of t dt. So now, if g is found by doing the antiderivative of f, isn't this graph kind of like the derivative of g? If we have to do the antiderivative to find things about g, this really is the graph of f prime for g of x. So it's a clever way to do the same thing that we just did. And in fact, they ask us to find two values. I'll split my paper in half. Traditionally, the first value has less work than the second value, but that's not always the case. Let's try them. G of 2. Well, this one's nicer because they gave us an equation. We don't have to manipulate the fundamental theorem here. It's just the integral from 1 to 2 of f of t dt. Cool. How do we find that? Well, we're not going to do the antiderivative. We don't have an equation, so this must measure the area from 1 to 2. Zooming in over here, my area from 1 to 2 is this little triangle. The base is certainly 1, but what about the height? Well, you can notice, I think, that our slope here goes down 1, and then over, look at that distance, over 2. So, doesn't that mean then that this point is halfway down there? Right? If this is -1 and this is 0, I think that point has to go down halfway. Another way you could think about it is you could divide each of these in 2, which means we go down 0.5 and over 1. Regardless of how you want to think about it, this is certainly 0.5. You'll also notice that I don't call it -0.5. You can if you would like. I just keep my areas positive. Do 1/2, base of 1, height is 1/2, that's in green, and then say, okay, the area is below the x-axis, there's going to be a negative. Right? That's all I do for it. I think it makes life a little bit easier. So what do we end up with? Well, it was -1/2 by 1 by 1/2, and so I think that tells us then that g of 2 is -1/4. Go S. What about g of -2? Pretty similar to before, but g of -2 has one weirdness in it, in that we're not going from least to greatest. I always like that to happen. I like to work from left to right, so we're going to switch the limits of integration. Forgot my dt over here, and if we switch, we need a negative. Don't forget that the negative does apply to the entirety, so it's going to be negative times whatever this area is, and that'll become very important right now. So we have negative. How do we determine this integral? Well, it is the area from -2 to 1. Looking at this guy over here, -2 all the way over to 1. Well, I see two areas. We have a triangle first. The base is 1. The height is 3. So, and it's above the x-axis. That looks like 3/2. And I also see a semicircle with a radius of 1. So our area will be half of a full circle, pi times the radius squared. And we're below the x-axis, so I think we need a negative on there. 1 squared is 1. 1 times pi is pi. That looks like -pi/2. 3/2 and -pi/2. Okay, well, let's put it all together. We have that 3/2 that I did in blue and a -pi/2. I would actually suggest you stop there. There's no reason to distribute the negative or put these terms together with the common denominator. This is something you can type into your phone or into any scientific calculator. Therefore, that is the answer we could stop at. Now, could you simplify it more? Sure. Just remember, if you make a mistake somewhere, you will get penalized and you will lose points, right? We could put this all together. You could distribute the negative, but I'd say that's probably just fine for now. Also, please be very careful about your parentheses. If you wrote this like this, and you said, oh, there's a negative and there's a negative here, and then you stopped here, you're wrong, right? Because this says -3/2 minus pi/2. It needs to be the negation of that entire area. The 3/2 becomes negative, the pi/2 becomes positive. All right, let's scoot on down. For each of g prime of -3 and g double prime of -3, find the value or state that it does not exist. All right, well, we have an equation, and they're asking us about other equations, g prime and g double prime. General rule of thumb is if you're going to find a value from an equation not given, you do need to state the equation first. How do we state the equation? Well, to go from g to g prime, we better take that derivative. Now, I'll split this in half again. You do not need to show this first step that I'm doing where I'm taking the derivative of each side by doing d dx. I like to do it just so I remember what the heck is actually happening here, but most people will skip this and they'll say, I can do the derivative in my head. The derivative of g is g prime, and the derivative of an integral, remember that's like our fundamental theorem part 2. They undo each other. If there's a variable on the top, it gets substituted in. Technically, we multiply by x, which is just 1, but there we go. And now we see that the derivative of g is f of x, right? This is why this graph belongs in this section. This is the derivative of g, f or g prime. There it is. Now what? Well, they asked for g prime of negative 3. So g prime of negative 3 is found by doing f of negative 3. This is the graph of f. F of negative 3 is just the point on the graph. Looking over here, f of negative 3 is this point up above, negative 3 comma something. You can look over and say, oh, that looks like 2, and you'd be right in this case. You could also use the slope to help you out. You could see that you go up 2 and over 2. So we could reduce that down and go up 1 over 1. Adding 1 to each of those gets us the point negative 3 comma 2. All right, so found the first one. Let's look at the second. Second one asks us for g double prime of negative 3. You could go through those same steps, right? d dx of g prime will find us g double prime. Okay, so we have g double prime of x is equal to f prime of x. Always good to find those equations first. Oftentimes you get points for finding those equations, and if you don't find them, you don't get the points. And then we find g double prime of negative 3, which is f prime of negative 3. Going back up to that same spot, I don't think there was a sharp point there, was there? No, I think everything looks a-okay. This is just a point on the line. And if we're asking for g double prime, which is f prime is the slope at this point. So f prime of negative 3, we already saw that the slope was up 2 over 2, up 1 over 1, or just 1. Right? The slope of that line is 1. Cool. Find the x-coordinate of each point at which the graph of g has a horizontal tangent. For each of these points, determine relative min, max, neither. Okay, let's break it down. Each point where g has a horizontal tangent. Horizontal tangents, picture that, side to side, are lines with a slope of, we always have to relate it back to slope or area, it's calculus, with a slope of 0. So to determine the x-coordinates where g has a horizontal tangent, we need to set g prime of x equal to 0. Not bad at all. Where is g prime equal to 0? Well, what is g prime? Oh, g prime is f of x. We stated that earlier. So really what they're saying here is, where is f of x equal to 0? Well, f of x is the graph. Where is a graph equal to 0 means where are the zeros of our graph? Zeros of a graph are where the graph touches or crosses the x-axis. I see 2 of them, negative 1 and 1. All right, so x equals negative 1 and 1. Those are the x-coordinates where g has horizontal tangents. All right, what's next? Relative min, max, or neither. I sense a sign chart. So we're going to go through. I'll do it over here if you want. Nah, it doesn't really matter. We'll just keep it consistent. Okay. So we have g prime of x equal to f of x. We know we have 2 of these, negative 1 and 1, which caused those equations to be 0. We're also looking on the interval from negative 4 to 3. We'll throw that on there. There we go. And then how do we determine the signs of g prime? Well, we look at the signs of f. The signs of f are above and below. I see above, positive, negative, negative. Positive, negative, negative. I hope we can remember that. Let's get back to it. Positive, negative, negative. All right, I'm going to do the graph of g in green. The graph of g will first increase and then decrease to the rest. All right. Once we're here, I think we can go ahead and do our conclusions. Okay, hopefully this is nothing too terrible. X equals -1 is a relative max because, and I like to put both of these here, g prime of x, which we don't know too much about, but we know that's equals f of x, changes from positive to negative. Great. What about the other one? Well, this other guy down here, x equals 1, is neither a relative min nor max because g prime of x, which equals f of x, does not change sign. And by the way, my handwriting is getting sloppy as we go through here. If you have extra time, and a lot of times you will have extra time on the free responses, either you flew through them or there's just parts you don't know how to answer and you're just sitting around twiddling your thumbs, go back and look at your handwriting. If your handwriting is just awful and you're like, what does that word say? Just rewrite it. Or even better, if you still don't like it, cross it out and just rewrite it up above. Make it look good though. If we can't read a number, we can't give you points for that number. All right, 3 problems to go, and they actually all somewhat connect to each other. So let's see what we can do. For -4 to 3, find all values of x for which the graph g has a point of inflection. We've done this before, and we've already found g double prime, which is in charge of our inflection and concavity. So g double prime of x is the same as f prime of x, and we want to determine where each of those are 0 or do not exist. So, looking at this, we'll just put it all together, or does not exist. Let's go ahead and list those values. Where is the slope 0? Well, jumping up here, we'll erase kind of all of our extra marks. Looks like we only have one slope of 0, one horizontal tangent, easy way to tell, right? That smooth curve at 0. And then the slope does not exist at 1, 2, 3 other places. -2, -1, 0, and 1, easy enough. So let's go ahead and put those all together. So -2, -1, 0, and 1. But don't forget, we don't know if those are inflection points yet without checking our sign chart. We're going from -4 to 3, -2, -1, 0, and 1. I think the only one of these that were 0 were that guy. The others were all our DNEs. And again, you don't have to waste time doing this on the test, but if it makes you happy, nothing wrong with writing in where the slope doesn't exist. Something like this. And then how do we determine where this doesn't exist? Well, we need to either look at g double prime, which we don't have, or f prime, which we don't have. So I guess we have to look at f to see the signs of f prime. Here is f, and it looks to me like we are increasing on these 2 intervals, and then we're decreasing everywhere else, right? Okay. So we go positive, negative, negative, positive, negative. Positive, negative, negative, positive, negative. And so that shows us that G, which I'm still doing in green, is concave up, then down for a while, then up, then down. So I see 1, 2, 3 inflection points. How do we justify this? Well, we say something like G has points of inflection at x equals -2, 0, and 1 because, and this is a little bit tricky here, I'm going to include this part. So we could say because g double prime of x equals f prime of x and f of x changes, and this is the same as before, from increasing to decreasing or vice versa at x equals -2, 0, and 1. Right? Going through this, I wanted to explain how we used the graph given to find that, but we also needed to connect f, or f prime, to g as well, which we did over here, and you could probably get away with it without putting that there, but you should put it somewhere. All right, find all intervals on the graph of g where g is increasing and concave down. This sounds like a sweet double sign chart, and this double sign chart is going to be really easy to put together because we've already done both of the single sign charts. -4 and 3. It's these same 4 points because -1 and 1 are included there, so that's very nice. So -2, -1, 0, 1. And then we have the same things before, right? And I'm just going to do straight down in the interest of time, and then -1 and 1. Those are kind of my intervals, right? And then we had a few things going on. We had G double prime, which was F prime. And then we also had G prime, which was F of X. And then we went through and filled these in. Looking up above, we saw we went positive, negative, negative. And then the second part was positive, negative, negative, positive, negative. Awesome. Well, let's just start. And I find when we have to do these doubles, I find it's easier to take each one individually. So I'll start with where G is increasing. Now this is an interval instead of a specific point that we've done before. G is increasing on the interval from -4 to -1. You do not have to include the endpoints here. In fact, we probably wouldn't because they said don't, but I'm going to anyways. I like increasing, decreasing, including endpoints. It makes more logical sense to me. So I'll say G is increasing on -4 to -1 because G prime of X equals F of X, and F of X is positive on -4 to -1. That's what our sign chart tells us. The second one is our concave down. So we'd say G is concave down on open intervals usually for concavity. So concave down from -2 to -1, -1 to 0, and 1 to 3 because G double prime of X equals F prime of X. And, well, how do we know it's concave down? You could say F prime of X is negative there, but we don't have the graph of F prime. So instead, how did we know that F prime is negative on these two intervals? It's because F is decreasing, right? So, and F is decreasing. Great. What does it say? On those intervals. Once we've justified where G is increasing and where G is concave down, the rest of this is just putting those two things together. We've already done the justifications. We just need to actually state the interval. Where is the interval? Well, increasing is this whole guy, and concave down are these and this. I think the only overlap is this space right here, isn't it, from -2 to -1? So we'd say something like, therefore, G is increasing and concave down on -2 to -1. Easy. We did the justifications earlier, then we just need one sentence to finish it off. Last but not least, find the absolute max and absolute min of G. We've done this before too. This won't be bad. Our candidates test. What are my candidates? Well, certainly we have the endpoints. How many critical points? We found 2 critical points earlier, and looking at these critical points, you can be pretty darn convinced that -1 is the absolute max and that the absolute min has to occur at one of these two. But it's by the time you explain to the graders how you know -1 has to be the absolute max and you eliminate this +1, honestly, the candidates test is just faster instead of writing a sentence. If there was just a single critical point, we could make this a little bit more efficient, but I'd say candidates test is easy enough here. -1 and 1. All right. For these, then I think we need to actually go and find the value of g of x, but don't forget we have an equation for g of x, which makes this a little easier. G of -4 is the integral from, and looking up above, the integral starts at 1, so we're going from 1 to -4 of f of t dt. Don't forget, we're going to switch that, -4 to 1, and now we just need the area. So from -4 to 1, it's unfortunate that I erased all of these areas, but that's okay. We can do all the individual ones again if you would like. So we knew that this area right here was 3/2. This guy down below was -pi/2. We might as well finish off the rest of these areas while I'm here. This area looks to be a trapezoid, right? And when we do a trapezoid, we have our parallel bases, 1 and 3, and then our height, if it's turned sideways, which is 2. So we do the average of the bases times the height, and that gives us 4. Alrighty, looks pretty good there. We might as well do the last triangle. We'll probably need it at some point. Base of 2, height of 1, below the x-axis, so the area is negative 1/2 times the base times the height, and that looks like negative 1. There we go. So we have all of these now. What were we asked to find? We were asked to find from negative 4 all the way over to 1. So it's just all of these added up, isn't it? 4 plus 3/2 minus pi over 2. So jumping down here, we have 4 plus 3/2 minus pi over 2. Did you see what I forgot? That negative, yeah? Did you see what I forgot a second time? Oh yeah, those parentheses. Because we're going to have to determine if this value is bigger or smaller, I'm going to put all of these over 2. So 4 is 8 over 2. And then we'll put all this together. 8 and 3 is 11. I'm getting 11 minus pi over 2 with a negative out front. So negative 11 minus pi over 2. All right, the rest of these go faster, I promise. G of negative 1. The reason I know they go faster is because now we're just going from 1 to numbers closer to 1, so there's less area that we have to measure. We do want to flip these again. And I think if I remember correctly, negative 1 to 1 is just the semicircle, isn't it? So it becomes negative pi over 2. Don't forget that second negative. It's positive pi over 2. G of 1 is very quick. We're going from 1 to itself. And whenever you measure the area of a point to itself, the area is always 0. Last but not least, G of 3. 1 to 3, we're finally going in the right direction. Don't forget that this was the area of our triangle, which I think we found was negative 1 here. All right, so then the question becomes, which one is the absolute min, which is the absolute max? Well, it looks to me like there's only one positive answer here. That's pi over 2. That's got to be our absolute max. And that also agrees with the sign chart from earlier, doesn't it? Right, the absolute max had to occur at negative 1. Looks pretty good. What about the min? That sign chart tells us the min is going to be at one of the two endpoints. Which endpoint is more minimal? Which one is smaller? Negative 1. Let's do that engineering rounding again. 11 minus 3 is 8. 8 over 2 is 4. This looks like negative 4. Negative 4 is certainly more negative than negative 1. And we're good to go. At the end of each lesson, you are going to be asked to record 3 important tricks that you need to remember to be successful in this type of free response. So this is where you look back through all of this and you think, what did I need to remember? And if you want to list more than 3, that's not a bad thing. While you're doing that, I'm going to take you through our conclusion, which is actually at the beginning. What do you need to do with interpreting graphs of f prime? Well, you need to identify where f of x is increasing or decreasing, and that's really meaning, does f have a positive or negative slope? We do that by looking at f prime of x, which will be given to you. You make a sign chart. You need to be able to find and justify values using the first or second derivative to test those values. We'll look at the second derivative test later on, but it is important to review. You need to find and justify points of inflection. Those are the slopes of f prime. Right? And we need to make sure not only to set f double prime equal to 0 and find where it doesn't exist, but also make sure that f double prime changes sign there. You need to find the values of f double prime from f prime. Try to use one-sided limits if your justifying does not exist. Find the values of f of x from an initial condition. That's manipulating the fundamental theorem. Write the equation of a tangent line. Pretty easy. We did that at the end of the 2017 one. Use a graph with common shapes to find the area under the graph. Today we did circles, triangles, and trapezoids. Don't forget that critical points are anywhere f prime is 0 or undefined, and bam, you found them. Inflection points have that additional burden of proof, right? Make sure f double prime changes sign. If you can conquer that, if you can feel comfortable on this, you really should walk away with 9 points, right? This one doesn't throw too many curveballs at you. You just need to be comfortable with the idea of using the graph of f prime to tell the reader about f. Join us next time for our targeted review number 2.